Okay, so welcome back to another video. Today we have a trigonometric integral where our bounds are symmetric, negative pi over 4 to pi over 4, and inside of our integral is the integrand, the square root of cosine of x minus sine of x dx. So as you might be guessing with something with, trigonometric functions, you think we actually have to use some sort of, trig identities to do the substitution, which you would be correct on that. And as something as complex as this, not only will the identities be used, some also special functions will be utilizing into our work as well. Specifically, we're going to be using the beta function and also the gamma function as well to simplify things. However, our answer for /value to our integral is not as, some kind of, simple number as you think. It's going to be like in a form of just a bunch of, special values number combined together into one answer. So that's just something to just look out for. So anyways, with all that being said, I think I pretty much just gave the big thing we'll be using, of course, is the trig identities to do our starting point. So why don't we actually jump right in? Okay, so before we actually do our using our trig identities, let's actually first do a nice little u-sub. So we're gonna let u equals x and then add this with pi divided by 4. So then that will mean that du is going to equal dx. So now we actually just plug all this back in, and then also we have for x, so we have to solve that by itself. So basically just subtract the pi over 4 to both sides. And we also have to change our bounds of integration now that we're in the world of u. So with all this all together, so now putting this back, we have our new bound. So we're gonna have 0, and then our top bound is gonna be pi divided by 2. And then inside of our square root, so inside is gonna be cosine of u subtract pi divided by 4. And then subtract sine of u minus pi divided by 4. So we're just going to close that off. And then over here is, of course, going to be the new differential du. So inside of the parameters of both our cosine and sine functions, this is when we're going to be using our little nice identities that we'll be using, the sums and differences of cosine and our sine angles. So let's actually just recall some of these formulas. So first I have that cosine for two values, a subtract b, is going to be, of course, we're going to have this is going to be cosine of angle A multiply with cosine of b. Then we're going to add this with sine of A and then sine of b. So now the second formula we'll be using, of course, is there's a sign over here. So sine of the difference. So disregard the addition that I just said, the sums of the angles. So we have sine of A subtract b is then our formula is going to be sine of A multiplied by cosine of b, then subtract with cosine of A and then multiply by sine of b. So with that being the case, we can actually just substitute some of our our values into the formula over here. So now we have that sine of u subtract pi divided by 4, that is going to be equal to, so sine of u, and then we have to evaluate this as, cosine of pi divided by 4, which that's just going to be, so I'm just going to leave this as 1 divided by the square root of 2, then subtract cosine of u, and then evaluate as sine of b, in this case pi over 4, so sine of pi over 4 is still going to be 1 divided by the square root of 2. And then just do the same thing for the other one. So now cosine of u subtract pi divided by 4. So then we're going to have that is going to be cosine of u multiplied by cosine of pi divided by 4. So that's going to be 1 divided by square root of 2. Then next is going to be plus sine of u, and then multiply by sine of pi over 4, which of course that's going to be 1 divided by square root of 2. So all those formulas in mind, so now we can actually rewrite our formula over here. So we have the integral from 0 to pi divided by 2. So now this is going to yield us with, so now the square root of, put this back together. So now I have cosine of u divided by square root of 2. Then add this with sine of u divided by the square root of 2. So close that off. And then we subtract. So now we have sine of u divided by square root of 2. And then next is cosine of u divided by the square root of 2. Then close that off, du, and then as you notice that we have some terms that go and cancel. So the sine of u and then the square root of 2 divided by square root of 2, this is going to cancel and then distribute the negative over here. So add those two together and we have a double. So with that in mind, so actually let me go back to the other color. So now reducing all this down, we're going to have the, 0 to pi divided by 2 of our bounds. So we have the square root of 2 cosine of u and then divided by the square root of 2 and then du. So with that being the case, I can actually, take the squares of both the numerator and denominator over here. Those are just constants, and jumping one step ahead, I can actually factor that outside of our integral since that's also a constant as well. So that would mean squaring this, I have the square root of 2, and then the square root of the square root of 2 over here would be the fourth root of 2. Yep, the fourth root of 2, and so factor that out and actually simplify it down because it's division. So now we would have the fourth root of 2 and then multiply by the integral from 0 to pi over 2 of the square root of cosine of u and then du. All right, so this is something as we can come down to reduce, and of course that's not as easy of an antiderivative to solve for, rather even just finding the definite integral on its own right. So now what do we actually do in order to evaluate our integrand? So that's where I mentioned the special formulas are going to be coming up. So both our gamma and beta functions. But first we're going to actually be using the beta function. So the beta function we have is that, let's see, right here is going to be a good spot to write. So we have our parameters b and n. So I'll just write this as capital B of m and n. So we have that it's the following trigonometric integral representation written as 2 times the integral from 0 to pi divided by 2 of sine of 2n minus 1, the power 2n minus 1 of theta, and then multiplied by cosine of the power 2n minus 1 theta, and then d theta, which of course we have that the real part of m and the real part of n have to be strictly greater than 0. So with this being the case, and of course, if we actually solve for the parameters itself, if you actually solve all this, so if we want to, I can actually just jump in or write this out. So I have the fourth root of 2. So then the integral from, let's see, it's going to be from 0 to pi divided by 2. And then we just fill in the gaps. If you actually just solve, so we don't have a sign, so that means we just set the exponent equal to 0. And then you plug in the gaps, so that means that have sine and then 2 to the power, or 2 times 1/2, and then minus 1 of u, and then cosine. So we just solve for this exponent, that's going to be 1/2. So set that equal to the 2n minus 1 equals 1/2. So we just fill in that. So that means you solve that, you have 2 times 3 divided by 4, and then subtract 1 u and then du. Then if we just reduce this, and don't forget there's a 2, so we have to divide that 2 to both sides. So now I have the fourth root of 2, and then divided by 2 is then multiply with our parameters b, beta function. So we have 1/2 and then comma 3 divided by 4. Okay, so those are our two values that we'll be using over here. And before we continue further, we are going to be using another beta function. In the formula is represented in terms of the gamma function. So we have that b sub n and n is going to equal to the following gamma representation. There's going to be gamma of n of gamma of m, and then multiply with gamma of n. Then divided by, you just take in those the sums of those values, m plus n. And so with that in mind, so let's keep going forward over here. Then we have that, just to reduce this even further, so I have the fourth root of 2 and then divided by 2, and then now we just plug in whatever those gamma representation based on that. So we have gamma of 1/2, then times gamma of 3 divided by 4, and then divided by, so gamma, and then you just add those sums together, which is going to be 5 divided by 4. And it's also worth noting that a special formula, gamma of 1/2, we know that if you actually just use its integral representation and solve it further, we just know that this simply is just going to equal to just the square root of pi. So that's actually a value that we can actually solve easily. So keep going is that we actually have another formula we'll be using in terms of everything's in terms of gamma, which is the Euler's reflection formula, and the second formula we're using is written as follows. So first, reflection formula is that gamma of 1 minus x then times gamma of x is going to equal to pi divided by sine of, so what is this? This is going to be, was it pi times x? So this being, of course, that x is not the integer, is not an integer. Just keep that in mind. That's the specific parameter that actually follows through with the rule. And another equation we'll be using in terms of gamma is that gamma of 1 plus x. So 1 plus x is the same thing written as x times gamma of x. So with this in mind, so now to continue forward with the formula, so let's see, we'll go this way over here. Okay, so everything so far, so it's going to be the fourth root of 2 divided by 2, and then multiplied by, so gamma 1/2 is of course going to be the square root of pi, and then that's still just going to remain as gamma of 3 over 4 for now. And then 5 over 4, we can actually just use this formula over here. We see that this is the same thing if I plug x equals 1 over 4. So now this is going to be 1 divided by 4 times gamma of 1 divided by 4. Okay, and then let me actually reduce this down a little further. So I have 1 over 4 over here, and then so basically putting this all together, I'm going to have 2 times the 4th root of 2. And then now we're just left with, so times square root of pi, and then gamma of 3 divided by 4. And then under the denominator is going to be gamma of 1 divided by 4. Okay, so with this, so we can actually now use the Euler's reflection formula to actually plug that formula in. So if I let 1 over 4 be x over here, so that means that's going to be gamma of 3 over 4, and then times gamma of 1 divided by 4. So then that's just going to equal to pi then divided by sine of pi divided by 4. And then that being, of course, pi over 4, sine of pi over 4 is going to be 1 divided by the square root of 2. However, I have a gamma over 1 over 4 in the denominator, so why don't we actually solve this a little bit differently? So rearranging the equation a little bit differently, I'm going to have that 1 divided by gamma of 1 over 4 is going to equal to gamma of 3 divided by 4, and then multiply by, so let me keep this as sine of pi over 4 first, and then divided by pi. So with that, and then of course sine of pi over 4 is going to be the 1 divided by the square root of 2. So now we actually just plug that back into, where is it? Over here. So this is going to lead us with, so far it's going to be, well, rather over here is where I'm pointing at. I forgot I wrote that side. So I have 2 and then times the 4th root of 2. And then we're gonna still, of course, that's still multiplied by pi. And then we actually have gamma square of 3 divided by 4 as we actually just put back the substitution back into over here, and then multiply by, so let's see, 1 divided by square root of 2, and then there's still the pi outside. Okay, so with that being in mind, so now we're almost done. We can actually finally reduce this. So this step is pretty self-explanatory to do, since you could actually just move all the square root of 2's together into 1, and then put it back into like a single, radical for specifically the 4th root, but then putting that all together, and then there's the square root of pi divided by pi, which of course the denominator is going to be square root of pi. And so the final answer is simply just going to be written as the 4th root of 8 divided by the square root of pi multiplied by gamma square at the value 3 over 4. So with that is our final answer. And as I mentioned, it's not as of a simple number that you would have thought of based on, just looking at this integral. So it's got something of, the gamma function of so that just puts everything, into some sort of, another perspective that it's not always, a number. Rather, it's just some close form of a bunch of formulas and numbers together at the same time that, of course, gamma has to come down to some number, but written into this close form. So there we have it. So yeah, that's pretty cool if you ask me.